Hello, welcome to another module in this massive open online course. So, we are looking at the basics of convex optimization. In particular, we have looked at the concept of convex sets, hyperplanes and hyperspaces, and we are looking at applications of these concepts in wireless communication, that is practical applications of these concepts, alright. So, today let us look at another application of the same concept, that is in multi-antenna beamforming, okay. So, what I want to look at is I want to introduce another application of the concept of hyperplanes and half spaces, and this is in the context of multi-antenna beamforming. And what happens in multi-antenna beamforming is basically you have a receiver with multiple antennas, correct, and let us say this is a receiver, wireless receiver in a wireless communication system, okay, and you have multiple antennas. Each of these is an antenna, and you have the signals that are coming with various channel coefficients, okay. So, you have the various channel coefficients corresponding to the antennas 1, 2 up to let us say L. So, there are a total of L antennas, and in this multi-antenna system what we have is we have these channel coefficients H1, H2 up to H1, H2 up to HL. These are the channel coefficients. These are also known as the feeding channel coefficients, because the wireless channel is typically a fading channel, that is the received power across the channel is varying with time, it is increasing and decreasing. So, the wireless channel coefficients are also known as fading channel coefficients, okay, and H1, H2, HL denote the L channel coefficients corresponding to the L antennas in this multi-antenna receiver, and this is also known as a single input multiple output or a CMO receiver, okay. So, this is also typically known as, such a system is also known as a CMO or a single input multiple output, in the sense we have multiple antennas. A single input multiple output system, and let us now assume the combining weight. So, H1, H2, HL are the channel coefficients. What we are going to do is we are going to combine the signals with weights W1, W2, WL. So, W1, W2, WL, you can think of these as the weights of the combiner. These are the weights of the combiner, these are the weights of combiner. Or you can also think of these as the beamformer, the weights of the combiner or also beamformer. And what we are performing is we would weigh the received signals and add them. So, we are performing a linear combination of the signals, and therefore, if you look at the effective gain of the signal gain across at the output of the combiner, that will be the weights times the corresponding channel coefficient and the sum. So, you can think of this as the effective, gain or the effective effective signal gain at the output of the combiner. And to normalize this effective signal gain, what we do is we set this equal to 1. So, typically what we have, what this implies is that we want to design a system such that this effective signal gain at the output of the combiner, that is, if we look at the output of the combiner, the effective signal gain is unity. Alright, so we would like to design such a combiner. This is typically a constraint in multiple antenna processing, one of the types of constraints that can be employed in multiple antenna processing. Okay. So, what we have is this can be written as H1, H2 up to HL, that is the channel coefficients. This is the vector H bar transpose times the vector, if you look at this, W1, W2, WL, this is equal to 1. You can call this as the beam forming vector, or this is basically also your receive beam former. So, H bar transpose W bar, where W bar is a vector of combining weights, or the combiner or the receive beam former is 1 to ensure unity gain, which basically implies H bar transpose W bar equals 1, and this you can see now is nothing but a hyperplane constraint. Okay. So, this is a practical application of the concept of hyperplane in a wireless communication system, which says that all these beam forming vectors W bar lie on this hyperplane described by H bar transpose W bar equals 1. This is the hyperplane constraint, and what this is doing is basically this is ensuring unity, gain for the desired user or desired signal. That is, what you are doing is you are ensuring that the gain, signal gain corresponding to a particular desired user or signal is unity at the output of the combiner. So, this signal is unity, and then what you can do is you can either suppress, you can typically either suppress the noise or suppress the interfering signals of the interfering user. So, this is typically a constraint that is employed in multi antenna signal processing in a wireless communication system. Alright. So, we have seen the definition, the notions of hyperplanes and half spaces. Let us now move on to different types of convex sets. In particular, let us look at spherical balls, or the norm, what are also known as norm balls. Okay. So, the next type of convex set we want to look at is that of a norm ball, or basically a Euclidean ball. So, what we want to look at is this constraint of a norm ball, in particular a Euclidean ball. And if you look at this, for instance, if you look at a ball in 2 dimensions, it is basically a circle with a certain center, let us say at the origin 0, and this has a radius r. Then if you look at any point in the interior of the circle x bar, if you look at norm, that is the length of this vector, which is norm of x bar, that has to naturally be less than or equal to r, which is the radius. Okay. So, this describes the interior of a circle, which is nothing but a two dimensional ball or a sphere. Interior of circle of radius equal to r, and with center origin. Now, if the center is not the origin, then you can simply shift it to the origin by considering norm x bar minus xc bar less than or equal to r. This is a general, this is a circle, or this is a circle or a sphere. In fact, you can, if x bar is an n dimensional vector, if we consider an n dimensional vector, this is a sphere or ball with center at xc bar. Okay. So, this describes the interior of an n dimensional ball with center xc bar and radius r. Okay. And this can be seen to be convex, and that can be briefly justified as follows, that is, this region is convex. For sake of simplicity, let us consider simply the ball with center at origin. Remember, if the ball with center at origin is convex, then naturally if you shift it to any center xc bar, it is also going to be convex, because shifting does not affect the convexity. Alright. So, if norm x bar less than equal to r is convex, the norm x bar minus xc bar less than equal to r is also convex, because translation does not affect the convexity of the object, convexity of the region, okay, or the set. Okay. And consider 2 points. To verify this, simply consider 2 points x1 bar. So, we have to demonstrate that given any 2 points x1 bar, x2 bar, their convex combination lies in the set. Consider x1 bar, x2 bar. Let us denote this set by B. Okay. Belong to B. Then what we have is, we have norm by definition, since they belong to the interior of the ball, norm x1 bar less than equal to r, norm x2 bar less than equal to r. Now, let us consider the convex combination. We have theta times norm theta times x1 bar plus 1 minus theta times x2 bar. We have to show that the norm of this is less than equal to r, so that this also lies in the interior of the ball. Now, you can readily see what needs to be done. First, we can use the triangle inequality. That is, norm a bar plus b, norm of a bar plus b bar is less than equal to norm a bar plus norm b bar. So, that gives me this is less than or equal to theta times x1 bar norm plus norm of 1 minus theta times x2 bar. Now, remember, theta is positive because this is a convex combination. So, we have 0 less than equal to theta less than equal to 1, which basically implies that theta comma 1 minus theta are both greater than or equal to 0. So, a norm of theta times x1 bar is theta times norm of x1 bar, because theta is greater than or equal to 0, plus 1 minus theta times norm of x2 bar, since 1 minus theta is also greater than or equal to 0. Now, observe that norm x1 bar, norm x2 bar are less than or equal to r. Remember, both these quantities lie in the interior of the ball, therefore, they are less than or equal to r. So, this is less than or equal to theta times r plus 1 minus theta times r, which is nothing but r. Okay. So, that implies you have norm of theta times x1 bar plus 1 minus theta times x2 bar less than or equal to r implies theta times x1 bar plus 1 minus theta times x2 bar less than or equal to r, which implies this is essentially belongs to the set B, which implies B is convex. Okay, that completes the proof. Okay, and that is obvious. What we have been able to show that if x1 bar for any 2 points x1 bar x2 bar belong to the ball, their convex combination, all their convex combinations also belong to the ball. Therefore, the norm ball is convex. Okay, and this norm ball, now remember another equivalent. So, we want to another equivalent way, an interesting way to represent this is, now we can represent this norm ball as B of xc bar comma r. So, this denotes a ball or norm ball with center equal to x bar c. I am sorry, this is not r bar, but this is r, which is the radius equal to r. So, this is the norm ball. Another equivalent way to represent the norm ball, that is an equivalent representation, is as follows. The equivalent representation equivalent representation of the norm ball is as follows. That would be, remember, norm of x bar minus xc bar equal to r, and this implies, you can write this as x bar minus xc bar is r times some vector u, correct, where norm of u bar is less than or equal to 1. For instance, I can always write this, if you look at this x bar, I can always write this x bar equals r times some vector u bar, correct, where u bar is unit vector in this direction, or u bar, norm of u bar is less than or equal to 1. Okay. So, the norm of u bar is less than or equal to 1. Okay. So, what that means is that is what this, and therefore, now you can see, and you can in fact readily verify this, this implies that norm of x bar minus xc bar equals norm of r of u bar. Since r is positive, this is r times norm of u bar, and norm u bar less than or equal to 1, which means this is less than or equal to r, which is the same thing, which is stating the same thing in a different way. That is, you are finding a vector u bar, and which is norm less than or equal to 1, and you are saying that x bar minus xc bar equals r times u bar, and this is true for any such vector u bar, since this norm of x bar minus xc bar is less than or equal to r. So, such point x bar will lie in the interior of the ball, which implies now that if you look at x bar equals x bar c plus r times u bar such that norm u bar less than or equal to 1, this lies in the this lies in the interior of the ball. This implies that I can represent the ball with the center xc bar comma radius r also in the following form, that is equal to the set of all vectors x bar c plus r u bar such that norm u bar is less than or equal to so this is an alternative representation of the norm ball, or this is basically an alternative representation of the norm ball. This is alternative representation of the norm ball. Okay. All right. So, that is x bar, x c bar, that is center, plus r the radius times u bar, where u bar is any vector such that norm u bar is less than or equal to. Okay. So, this is an alternative representation which is very convenient to represent, oftentimes to represent the norm ball. Okay. Alright, so let us look at another application similar to what we have seen for the hyperplanes and half spaces. Let us again look at an application of the concept of norm ball for wireless. Application of the concept of norm ball in a wireless system, and this can be seen as follows. For instance, again let us go back to our multi antenna beam forming problem. And we again have the different signals. So, this is again your multi antenna receiver, and these are antennas 1, 2 up to antennas L, and which we are combining using our beam forming using the weights W1, W2 up to WL. Remember or recall that these are the beam forming weights. These are the beam forming weights, and what we will ensure that if you look at the energy of the beam former, that is W1 square plus W2 square, because this also influences the power, the output power of the combiner. So, we restrict the energy of the beam former, which is equal to the energy of the beam former, and often also called the power of the beam former, because this is what is applied at every time instant, energy slash power of beam former. Now, in any wireless communication system, this has to be suitably restricted, because this influences the power of the signal at the output of the beamformer. If the energy of the beamformer is unbounded, then the power of the output signal can also be unbounded. Therefore, to ensure a stable beamformer, we restrict this energy of the beamformer typically to unity. Alright. So, in any wireless communication system, energy of the beamformer has to be limited. Let us call this as the power, because that is typically the nomenclature that is used. The power of the beamformer has to be limited. Now, if you can look at this, this is nothing but norm of W bar square. This is norm of W bar square. Typically, this is set less than or equal to unity. So, we have the constraint norm of W bar square less than or equal to unity, which implies that if you look at this, this implies that norm of W bar has to be less than or equal to unity, and this is nothing but a norm ball constraint. So, this is the beamformer power constraint, which is a norm ball constraint, norm of W bar, that is constrains the set of all beamformers to a norm ball with radius 1, to interior of a norm ball with radius 1. So, this is a norm ball constraint. So, this is the constraint on the beamformer power constraint. This can also be thought of as the beamformer power constraint, which is basically nothing but a norm ball or a Euclidean ball constraint. Alright, so that is an interesting application of the concept of a norm ball to a wireless communication scenario to design the constraint for a receive beamformer. Alright, so we have seen various other concepts in this module, namely that of the norm ball or the Euclidean ball and its application in the context of a wireless communication system. So, we will stop here and continue in the subsequent modules. Thank you very much.